All right, 12 o'clock. Go ahead and get started. As Stacy mentioned in the chat box, Hippocampus has not been working. I did receive an email from a different faculty member this morning, so you can't use that to access videos. There are different spots in the course where you can also access the videos. I will post the official spreadsheet that I use for videos. I think I might have posted that somewhere at the beginning of the semester, but I don't remember. So I'll post that in the announcements after class today, so you can have easy access to videos for the remainder of, well, the last week or so. So does anybody have any other questions before we jump into sections 27 and 28? No? Okay, well, we have two sections this week. 27 and 28 go very much hand in hand. So you're going to find that they're pretty nice. Both WebWork sections are relatively small, maybe 6 or 7 questions each, I think. So not too bad. We have an Excel assignment with exponential growth and decay, so hopefully that's not too bad for you. I don't think I have a video that goes with that. If you find that you need one, I would need that before Monday. So if you are requesting help for the Excel assignment, that needs to come in this week because Mondays are usually pretty busy, and I tend to not read a lot of email later in the day on Monday. You've got your weekly quiz and your weekly discussion board. So there's that. Okay, but this is the last week of new materials. All right, so Stacy, I'll mark that down. See if since you're requesting one now, I'll see if I have one, or if one is needed. I don't remember off the top of my head that Excel assignment. I did it at the beginning of the semester, but that was 15 weeks ago. So I'll double check, and if we need one or I'll make one, I'll see if I can get that done either later today or tomorrow, and I'll get that posted. So, okay. All right, so let's go ahead and jump in. As usual, feel free to jump in whenever you have questions. If you understood sections 23 and 24, just the overarching concepts of absolute and relative change, where if we had a positive change, that was an increase, and if we had a negative change, that was a decrease. If you understood that, we're going to continue that same kind of idea as we get into exponential growth and decay. Because as you can imagine, growth means we're increasing, decay means we're decreasing. So it's not huge concept shifts. Really, it's just a little bit different way of thinking about things. So here we are with exponential growth. Now, the overall formula that we're going to be dealing with is A equals A sub 0, and I'm going to tell you what all this stuff means. Inside parentheses is the growth factor GF raised to the T. And this looks so ridiculously foreign when you just throw these things out here that it just doesn't make any sense. So what we're going to do is we're going to talk about each one of these pieces. So this is the ending amount. And if you want to change, the letters in yours to make it make sense for you, do that. So we have the ending amount here with this letter A. This A sub 0, it's A naught, is a lot of the way that math people talk about this. This is your initial amount. So how much are we starting with? All right, so our initial amount. Then we have inside parentheses, this GF is called our growth factor. Now, we're going to talk about our growth factor more in just a minute. But inside the parentheses is the growth factor, and then here at the T, I'm sure you could have all guessed, represents time. Now that time can be anything. That time could be days, months, years, 6-month chunks, 10-minute intervals. It doesn't matter. It simply is the time period that we're talking about in terms of growth. All right, so this is our basic formula that we're going to use. So if we know our growth factor, it goes inside the parentheses, our initial amount is being multiplied, right? Because this A sub 0 will be a number. So we'll have a number times the parentheses raised to the exponent. All right, so there's kind of the basic overarching. Now let's go ahead and talk about this growth factor. Okay, I'm stalling just a minute in case anybody's writing things down. Everybody good? Okay, growth factor. So the growth factor, if you recall, right, so our formula, ending amount is the initial amount times our growth factor raised to the t power. Well, that growth factor can be found in a couple of different ways. One way is to take 1 plus the percent increase. And I know what you're thinking. Oh my gosh, that's very similar to compound interest, because I know you guys make the connections to stuff we've already done. I know you do. So this 1 plus the percent increase is very much, it's very similar to compound interest, what I just said. Yep. Another way to find the growth factor is to take the new value and divide by the old value. So if they give you 2 consecutive values, that might be the way to go. But generally, this is what we see. Now, I want to throw one other thing at you, right? Sometimes I feel like I'm throwing bricks and seeing if you guys catch them or, get hit in the forehead. But if I would say that something, sorry, my phone's ringing. Let me ignore that. There we go. If I would say that something doubles, if something doubles, what does that mean in terms of mathematics? What does doubling mean? You multiply it by 2. Exactly. So if something doubles, that means that your growth factor is equal to 2, because as Amber said, you multiply by 2. Okay, think about if something triples. What does that mean? You multiply by 3. You're on a roll. Yeah, so then your growth factor would be 3. So we really have 3 ways to find the growth factor. Sometimes you have to do the math, like in options 1 or option 2, and there will be times where in the problem they will say, hey, blah, blah, blah doubles. Well, if it doubles, my growth factor is 2 because I would be multiplying by 2. All right, so hopefully that kind of thing makes sense logically, because a lot of times in math, if we can make sense of it logically, life is a little bit easier. So, okay, so let's keep, oh my gosh, excuse me, let's keep these things in mind as we move through to the next problem. I shouldn't say the next problem, it would be the first problem. So in this first problem, I'm going to make you suffer, maybe. I'm going to make you suffer by doing this chart. And the reason we're doing this, well, for a lot of reasons, part of it is to remember absolute and relative change. Now, I'm going to go ahead and cross out this first month, or this first week, because remember absolute change. Let me ask you, what is the formula to find absolute change? New minus old, very good. And what about relative change? Very good. New minus old divided by old. That stuff hopefully is fresh, right? Because you guys just did it, so good job there. Okay, so we have our formulas. Now, if we want to do that first week, the first week would be new, there's no old, right? So we can't find the absolute and relative change for those weeks. But for week 1, we can. So we're going to do week 1 together just to refresh, because I don't, it might have been a day since you've done this. But if we're in week 1, that means this is new and this is old. Okay, so I'm looking for the absolute change. How do I find the absolute change between weeks 0 and 1? We know it's new minus old. What value comes first? 14, exactly. So I take 14 minus 10. My absolute change is 4. Then, to find my relative change, I divide by old. My old value is 10. I change it to a decimal, change that to a percent because relative change is percent change, and I end up with 40%. Okay, right, there's your refresher from what we did last week, actually. I would like you to finish the table. So 2 and 3 in the table. And so that would give you part A. I want you to see if you can come up with B and C. Go ahead and just stop B and C after that. If you get stuck, that's okay too. See what you can do. And give me a yes or a whatever in the chat box when you're ready to chat. let's go ahead and what is your absolute change for week 2? Let's just go through the numbers real quick. 560, great. What about relative change? 40%. Now week 3, absolute change. 7.84, relative change. 40%. Good. Okay, so that's part 1 is filling in the table. What's the same? Absolute or relative change? Relative change is the same. Do you know what that tells you? We haven't talked about this yet, so I'm going to... Does anybody know what this tells them? Okay, you guys you're close. 40 is not exactly the growth factor, but it has something to do with the growth factor. Okay, so let's build on this. All right, so because we have, think about how this all relates. Because we have a consistent relative change, and we know that relative change is percent change, that means we know we have an exponential model. That's what it tells you just in general, right? You guys have gotten more detailed by going into the growth factor. But think about how you can tell this, because this is going to be important going forward. We know, we saw on that previous page that our growth factor is 1 plus the percent increase. And you know from section 23 and 24 that relative change is the same as percent change. So because we have a 40% change and it's positive, we know that's a percent increase. That gives me a growth factor. That means I have an exponential model. Because remember last week we did linear models, and there is a way from a table like this to be able to write a linear model as well. So we have to know the difference between them. Okay, so now that we know we have the exponential model, now we can go into the growth factor, which is part C. So the growth factor itself is not 40 because we're dealing with 1 plus the percent increase. Somebody typed it up. Stacy had it in there. Because if your percent increase is 40%, well, 40% as a decimal is 0.4. As you can see, my orange writing at the top. Therefore, my growth factor is 1.4. So it's 1 plus the percent increase. Because the 1 represents the 100%. 100% is what you started with, right? I started with everything, and then it grew. Okay? So, I mean, yeah, we'll get to that in a second. Okay, I was about getting ready to get ahead of myself. So now when we're ready to use a model for this, part D, let me change color because color is fun. If we're getting ready to start to write a model, A is our ending amount, equals, the next part is A sub 0, which is our initial amount. How much did we start with in this problem? 10, exactly. Think back to the linear models. Your y-intercept was your starting point when x is 0. With exponential models, your starting point still has an x value of 0. That is still a true statement. So our starting point is 10, and then as Stacy did, we have our growth factor in the middle, and we raise it to the t power, where t represents the number of weeks. Okay. So just like with linear models, you should have 2 variables. Look how I have 2 variables in my final model. I have the capital A representing ending amount, and I have the lowercase t, which represents my time period. Okay, let's jump to letter E. How am I going to do letter E? Use the model to predict for week 6. What am I going to do with that guy? Any ideas? T is 6. Yeah, you're talking about time. So I would say time is 6. So we go ahead in our model, 10 times 1.4 raised to the 6th power. And now it becomes an order of operations problem, right? Depending on your calculator, make sure you're careful with this. You do want to do the exponent first. So if you have to type this in pieces, you want to type in the 1.4 raised to the 6th power, get an answer. Last step is to multiply by 10. So at 6 weeks, how much money will we have? $75.30 is absolutely correct. Yep. Does anybody have any questions on where any of this stuff came from? Makes sense? See how when we got to the table, it was the relative change, gave us the exponential model, which gave us the growth factor. You see how it's all connected. Okay. I want you to try this one. So this one doesn't have a table. It just has a problem. Frogs increase at a rate of 32% every week. If there are currently 40 frogs around my pond, ... blah, blah, blah. Of course, this is completely and totally made up. I'm going to give you a minute or two, maybe 3. Go ahead and type yes in the box when you're either stuck or you have an answer. So, very interesting. Okay, so let's look at what this talks about. And actually, and Stacy, I'm not going to pick on you, but I'm totally going to use your answer in the chat box to talk about this, because students do this all the time, and I want to make sure that we don't get in this habit. Because while your mathematics is pretty darn good, we're missing some key pieces, and I want to make sure that we have all the pieces that are necessary, because you're going to lose points if you don't. And I want to make sure that we have all the pieces necessary. And oh, sure, blame caffeine. Yeah, that's a good one. That's a good one. All right. So frogs increase at a rate, right, 32%. If there are currently 40 frogs, write a model. Now, what I want to stress right here in part A, write a model means we should have 2 variables in our answer. Right? Linear models, exponential models, it doesn't matter. To write a model means to write an equation, and we have to have 2 unknown values, an input and an output, basically. Right? So think, we used X and Y in our linear models last week. This week we're using T for time and A for our ending amount. Those could just as easily be X and Y. It doesn't matter. It's just 2 variables. So when you're thinking about this, in our model, right, we know our model is A equals the initial amount. We've got our growth factor raised to our time. Do you know your ending amount in this problem? No. So we just start with A. What does the rest of it look like from there just for part A? There you go. We start with 40 frogs. There's my initial amount. My growth factor is 1 plus the percent increase, so 1.32. And then we're going to raise that to the t, which is time. And in this case, just like in the last problem, time is weeks. Okay, so in order to get credit for the model, you have to have something that looks very similar to that. I don't care if you use A and T, but it needs to be 2 variables, an ending amount and a time span. Then you jump down to letter B. So Stacy, your answer, which is in green at the top, is beautiful for part B, because you say 10 weeks, time is 10. So my ending amount, right, the mathematics that you need to do has a 10 in the place for T. But if you had used that for your answer for part A, you would be counted wrong, because the 10 is for one specific time period. Your model should show for any time period, which is why we have the variable T. So you got to make sure there's that very, thin line of difference. So, okay, but see, you've got the gist. I just wanted to point out those little nitpicky things that, I'm nitpicky about. I shouldn't say me. Mathematics is picky about. Okay, so when I plug in a 10 for this guy, how many frogs am I going to have after 10 weeks? 642, which I would go out and say is a lot of frogs. I mean, I don't know. And of course, this is all made up data, but if I had a pond, it would really freak me out if I went outside and there were 642 frogs jumping around. All right, questions so far? You guys doing okay? Have I lost anybody? Everybody still with me? Yeah. All right, good. Let's move on to exponential decay. Now, if you understood, okay, so that was section 27 in a nutshell. Exponential growth, section 27. Now we're going to do section 28, exponential decay. So if you can wrap your mind around what we just did in exponential growth, exponential decay shouldn't really seem all that different. So here's my formula. A equals my beginning amount, my decay factor raised to time. So notice the only difference is that instead of a growth factor, we have a decay factor. Now, if you think about how we found the growth factor, does anybody want to guess on how we're going to find the decay factor? Remember, the growth factor was 1 plus the percent increase. So what do you think the decay factor is going to be? Oh my gosh, fabulous. 1 minus the percent decrease, because it's going down, right? So we subtract. That's the only difference. So when you're reading the problem, if something goes up, you add to 1. If it goes down, you subtract from 1. That's basically it. So percent decrease, again, relative change is percent change. That's where that comes into play. We still have the idea of new divided by old, though we don't do that very much. We might get into the idea of half-life, where our decay factor would be half. That's a chemistry thing generally, but very similar to what we just did. I just hit the wrong button. I'm going to get there. There we go. Okay. So once again, absolute and relative change. I want you guys to do the table and see if you can do all B through D. I'm going to give you a few minutes. Go ahead and just click yes in the chat box when you're finished. Unless you're Stacy and you do whatever you want, that's fine too. Put whatever you want in the chat box when you're done. How about those directions? We'll go with that. All right, see what you can do. Okay, so we found the absolute relative change. Right, new minus old divided by old. We look at these and we notice the absolute change, which from section 23 and 24 is a constant number, right? Absolute change is a number. And when you look at this, it's different every time. So there is no reoccurring constant change. It's different every week. But you look at relative change, which is percent change, and that's the same every week. So if we look at our relative change column and it's the same, what does that tell you? So relative change is the same, and what does it tell you? Relative change is percent change. So if it's constant, that means we have an exponential model. That's what the same relative change means. Okay, so it means I have an exponential model. I can use my A equals A sub 0 times my either growth or decay factor, depending on the problem, times T. Now, how do I know in this problem I'm going to have a decay factor? What's the determining piece? Because you should be able to tell by looking. Well, Trish, you just found it. It's negative, exactly. So when you're looking at the relative change, because every one of them has a minus sign or a negative sign in front of it, yeah, because they're all negative, that means it's decreasing. And we know that if it's decreasing, that means decay, that means it's going down. In the last problem that we did with the table, remember, it was a 40%, it was positive, so we knew it was growing. That makes it a growth factor. So the decay factor in this case, which, let's see, Trisha already put it in there. The decay factor, remember, is 1 minus the percent change, which is 0.2. So that makes my decay factor what? What is 1 minus 0.2? 0.8, exactly. So my decay factor, oops, that's a D, is 0.8. Because you think about it, if it decreases by 20%, that means 80% is still there. That's what that tells you. Okay, so how do we write this as a model? What is my model? Oh, look at that. Stacy was ready for that question. A equals my initial amount of 120. My decay factor goes in the parentheses with a variable of T. Good. Where again, in this case, T represents number of weeks. And the last one, how much is left after 6 weeks? So again, just like in the last time, T is 6. So if I get 120 times 0.8, pardon that nastiness. Oh, make that a 6. That's horrible. What do you get after 6 weeks? 3146 is correct. Good. Any questions on that particular problem? Going once, going twice. Seeing how all these pieces go together. Hopefully. Okay. You guys try this one. Knowing that depreciates mean to decrease, right? So we're talking about a car. SUV depreciates 8% a year. If you bought a $26,000 SUV, ... All right. So you try this one. Give me a something in the chat box when you're ready. All right. So we're buying an SUV, costing a lot of money. What's our model to show the depreciation over years? So we start with 26,000. We end up with 0.92 raised to the t power. Good, because it decreases by 8%. So that's 1 minus 8%, which gives us the 9.2. Very good, very good. Jennifer, make sure, I think you miscalculated your 8% in yours. So you got to watch that, right? Yep, that's the only difference. Okay, so we have our model with two variables, which we know is a requirement. So then it said after 5 years. Where does that 5 go? 5 goes in for t. So 26,000 times 0.92 raised to the 5. So the 0.92 represents how much is still left each year, right? If it goes down by 8%, it still has 92% as its value. So yeah, the 5 years is time, it goes in for t. So we plug that in. After 5 years, how much is your SUV worth after 5 years? $17,136.12. Now, that's assuming you've kept it in good condition, you haven't run into any trees, your dogs haven't puked all over the interior, right? There are other things that go into the value of a car, but this is kind of your general idea. Okay. Questions. General questions over exponential growth or decay. General questions. The 5 of you that are here all seem to be, you're all participating, you all seem to know what's going on. That's positive. That's super positive. Okay, I think I have one more one more question here. So this one is a little bit different. You know, we come back with the table. So do this table, see how much you can do. When you get to the spot where you're either confused or you're done, let me know. We'll see what we can do. Okay, give you a few minutes. What we're doing, it's different. Hopefully you noticed that it was different and it wasn't exactly the same. So week 1, absolute change. 5, relative change. 25%. Yep. Week 2, absolute change. 5. Week 2, relative change. 20%. Week 3, absolute change. 5. Week 3, relative change. 17%. Okay, so that's letter A. What do you notice in this problem? What's the same? The absolute change, right? So the absolute change is now the same. And remember, the absolute change is a concrete number, and it's the same over and over and over. It's reoccurring, and it's always the same, and it's the same number. Where else have we seen that reoccurring same number, same change every time? Linear. Be more specific about linear. Which part of the linear model is reoccurring and it's always the same? The slope. The slope is the one that's reoccurring. Remember, the y-intercept is only there one time, but the slope reoccurs, and it's always the same. So when the absolute change is the same, that means we have the slope. Our slope is 5 because our 5 is the reoccurring constant change. Right? So when the absolute change is the same, we have linear. When the relative change is the same, we have exponential. You have to be able to differentiate between the two when you're looking at a model. Okay, so if I know absolute's the change, that gives me a linear model. I know my slope is 5 because that is the change. What does my model look like for this one? This is taking me back to last week. Do you remember how to write linear models from last week? Start with y equals. What comes next? 5x plus 20, absolutely. Slope is attached to the x value, and then we're adding our y-intercept. And our y-intercept is when x equals 0, and x represents time. So since time is in weeks, when weeks are 0, that's my y-intercept. So my model is y equals 5x plus 20. All right, after 8 weeks, where does that 8 go? Where the x, exactly. So x is 8. So y equals 5 times 8 plus 20. So mathematically, 40 plus 20 gives me what? 60. So after 8 weeks, the amount would be 60. So the process, right, you have to make sure you understand, am I following the linear process of thinking or the exponential? Because yes, it matters. Okay, so I like to throw that one in there because it looks the same as the other 2 problems that we did, but because on this one, the absolute change is the same, that gives us a linear model instead of an exponential model, which is drastically different. So there's that. Okay, who has questions about anything we did, exponential growth, exponential decay, or this last linear problem? Anybody have anything that's coming to mind? Not right now? Okay. Well, that's the mathematics of today. So let's remember, this is the last week of new stuff, right? So it's 27, 28, and it's over. Next is exam 3. Exam 3 is open. You can schedule it and take it anytime you want. So if you want to do all of your homework today and tomorrow for sections 27, 28 and take exam 3 on Friday and be done, knock yourselves out, right? You just have to make sure you schedule your exam. So if you haven't scheduled yet, do that now. Next week's live session, Tuesday from 12 to 1, will be questions, right? Whatever questions you have, I will be available. So I'll be in my office, I'll have my computer up. If you're just working on your exam and you don't have any questions, then you do not have to come, right? If you can pop in, I will be available the entire hour. So if you're working on stuff and at 12:40 you have a question, pop on, I'll be here. Okay? So it's up to you what you need. Of course, I will be available outside of that hour. You just have to shoot me an email and I will get back to you as soon as possible. So if you haven't scheduled your exam, please do that today so that you can get the day and the time that you want. And let me know what you need from me. Do not forget that Project 3 is also due next week. I don't know if you've started that yet, but it's due next week as well. So there's that. The practice test online, the online review quiz, is probably the best helpful tool to get you prepped for exam 3. Remember, you can do that as many times as you want, and the highest score is recorded. So if you have questions on that as you go, of course, shoot me an email on that too. And yeah, I'm here for you. So does anybody else have any other questions about anything before we sign off for today? And then I'll get things posted in the announcements so that you have some more resources. And of course, if you need anything else, you just got to let me know. So anything else for the good of the group? Gone once, gone twice, sold to another semester down. Keep up the good work. You got 2 weeks, week and a half left, and you're done. So push through, get it done. Let me know how I can help you, and good luck on your final exam. I'll see you guys later.